Hi guys, welcome to Laplace Academy, and today I'm going to talk about another major topics of Simscape fluids. Today I want to talk about the sensors, and in the previous tutorials you probably have seen that I have used some of these sensors, but I had not made a specific video on that topic, and now I'm going to cover everything that you're going to need to get started with sensors in MATLAB Simscape. So I'm going to start with an isothermal liquid system, and the first sensor I'm going to talk about is the flow rate sensor. So you can see that each of these tabs, for example, the gas has a sensor tab, and the isothermal liquid has a sensor, and the same goes for thermal liquids. It has a sensor part. Also the two-phase liquids, all of these modules have a sensors set of blocks, and the way to use them are basically the same. So there's not going to be too many differences between a two-phase fluid sensor and an isothermal liquid fluid sensor. So let's get started. I want to add an isothermal liquid reservoir, and I set it to a constant specified pressure of, let's say, 5 bars. This is my high pressure reservoir, and I'm going to make a copy of it and set it to 3 bars. So this differential pressure is going to make the fluid transmit from the high pressure source into the low pressure source. And I cannot connect them directly to each other. I need to have a flow resistance to make for this pressure differential. So under the elements tab, let's say I add a pipe. Okay, and that's it. Now, before I run the model, I need to add a solver configuration block, and under the utilities tab, an isothermal liquid properties. So let's run the model, and it's all right. But I want to know the flow rate, the volumetric flow rate that is going to be transmitted through this pipe. So I add a flow rate sensor, and before I connect it to my system, I want to double click on it, and you see I have two options here, basically three options. I have to choose between the mass flow rate or the volumetric flow rate, or both of them. I'm going to go for both of them, and you see the ports have changed. I have a mass flow rate physical signal port and a volumetric flow rate physical signal port. And in the description tab, it tells me about this sensor, and I want to let you know that the units here are in SI units. So the mass flow rate is going to be in kilograms per second, and the volumetric flow rate is going to be in cubic meters per second. So I have to make all of the fluid go through this sensor. So the pipe outlet is going to be connected to the sensor inlet, and the sensor outlet is going to be connected to my low pressure reservoir. Now all of the fluid has to pass through this sensor, and I add two PS Simulink converters just to be able to display the result. Okay, now I run the model by pressing Ctrl T. And this is the mass flow rate in kilograms per second, and this is the volumetric flow rate. And you can see that since the water density is almost 1000, if you multiply the volumetric flow rate by the water density, you will come with the mass flow rate. And Since this value is so small, it is in cubic meters per second, what if I want to see the result in cubic meters per hour? I should double click on the PS Simulink converter, and you can see that the output signal unit is inherited. It means that this converter is not going to change the units, and the units are set by this flow rate sensor. The flow rate sensor sends a signal in cubic meters per second, and the result is basically in cubic meters per second. For example, I type cubic meters per second, and if I run the model, the result is not going to change. But I want cubic meters per hour, so instead of seconds, I type H. And now you see there is a warning here. It means that this unit is not defined in MATLAB. The reason is that the hour is HR, not H. Now it is cubic meters per hour, and now I run it again, and you see the value has changed. It is now in cubic meters per hour. Basically multiplied the result by 3600. That is the conversion factor for cubic meters per second into cubic meters per hour. One point I want you to know is that neither this sensor nor any of other sensors that I'm going to talk about, they are not going to have any effect on the simulation results. So basically it means that this flow rate sensor is an ideal flow rate sensor. It exerts no pressure differential for the liquid, and it has no resistance. It is zero resistance, it is ideal, and having 1,000 of sensors is not going to change the result of your system. These are just displaying the values of the parameters of the fluid of the system, and they're not going to change the result. So feel free to add as many sensors as you like. They're not going to change any of the results. Next, I want to talk about the pressure sensors, and let's make a thermal liquid system out of that. I again am going to add a reservoir, maybe 2 reservoirs. Both of them are at atmospheric pressure, and currently I'm not going to change the temperature. And I want to add a flow rate source. So I set a constant volumetric flow rate source at 15 cubic meters per hour. Then I add pipe again. I set it to 100 meters, and I'm not going to change any of its settings. Now the system is complete. I only add a solver configuration and a thermal liquid settings block. I run the model and everything is perfectly fine. So this volumetric flow rate is an ideal source, and it definitely is going to transmit 15 cubic meters per hour. If you have any doubt about it, I can prove it to you. So I add a flow rate sensor. I set it as a volumetric flow rate. I make all the liquid pass through it. And having a PS Simulink converter in cubic meters per hour and a display block. I'm pretty much sure that the result is going to be 15 cubic meters per hour. And you see, that's right. But the question is, this flow rate source, which is going to transmit 15 cubic meters per hour, what is the differential pressure of this pump? And in order to answer that question, I need a pressure and temperature sensor. Now, if I double click on this block, I can see that I can check or uncheck the temperature and pressure. So I want the differential pressure, across this pump. I want to invert these two ports, the B and P ports. So I press Ctrl R, Ctrl I, Ctrl Shift R. Now this is better. Here again, I add a simulink converter and a display block. So the description says that the pressures are in Pascal. The unit is Pascal, so it's fine for now. And I run the model. And give me the result in pascals. You see the result is negative since, as the description says, the difference measurements are positive when the values at port A are greater than port B. So the outlet of this pump is high pressure. So the B port is having a higher pressure than the A port. And this means that if you want to make sure that the result is positive, you have to invert the sensor. And that's what I did right now by pressing Ctrl I. Now here, PA minus PB is going to be positive. So the result is not going to change, only the sign is going to be reverted. And that is the pressure increase across this pump. But this was the differential pressure. How about if you want the pressure of a single point? I make a copy of this pressure sensor, I invert it, and instead of difference, I set it to absolute. And now it asks for the pressure type. It has absolute pressure and gauge pressure. First, I set it to absolute pressure, and to see the result, I connect it to the outlet of this block. And since it is directly connected to my reservoir, which is at atmospheric pressure, I expect the output signal of this pressure sensor to be the atmospheric pressure. So I add a PS Simulink converter and the display block. Again, I'm going to repeat myself. This sensor is going to sense the pressure of this reservoir, and since it is at atmospheric pressure, I expect the result to be the pressure of atmosphere. And that is basically the result that I come with right here. And how about the gauge pressure? You probably know that the gauge pressure means the differential pressure between the atmosphere and the point of concern. So the gauge pressure of atmospheric pressure is basically 0. And if I run the model, I expect it to be 0. And that's it. Currently, I am using MATLAB version 2024b. But if you are using an older version of MATLAB, you probably do not have the luxury of selecting between all of these options for pressure sensors. So basically in the older versions like 2018, 2020, 2021, you can only select the differential pressure of any point. So it means that if you want to know the pressure of this point of the system, you have to connect the B port into somewhere. And the trick for that is that if you want to know the absolute pressure, you have to connect the sensor, the B port of the sensor, to the absolute reference of the system. So absolute reference means somewhere which has 0 pressure and 0 temperature. Now PA minus PB is going to be equal to PA, since absolute reference, it is somewhere which has the pressure and temperature equal to 0. You see now if I run the model, it is exactly the absolute pressure that I was going to expect. And if you want to find the gauge pressure, you need to make a copy of this reservoir. And now this sensor is going to display the differential pressure between port A and the atmosphere. This is exactly the definition of gauge pressure. And I expect it to display 0. And that's it. So that's the way to go for the previous versions of MATLAB. Okay, and now I'm going to talk about the temperature sensors. So I'm going to delete some of the blocks to make things easier to understand. And I delete these two. So in the pressure and temperature sensor, I make a copy and I uncheck the pressure and check temperature. Here you have a T port. It is going to display the temperature. And if I want the differential temperature between the ends of the pipe, I set the measurement reference to difference. Now I have 2 ports and I'm going to ask for TA minus TB across this pipe. Here's a PS Simulink converter and a display block. I run the model by pressing Ctrl T, and you see the value is basically 0 since this is an insulated pipe. It does not have that much of a heat transfer, and the reason why this is not 0 is because there's some friction in the system, and you can call it a negligible amount of differential temperature. So, but what if there's going to be some heat transfer in this pipe? I can use that in a thermal source block. And here's a heat flow rate source where I am going to add 2 megawatts of heat. And let me add the thermal reference here. So this block is basically going to add 2 megawatts of heat flow and add it to the fluid in the pipe. Now, if I run the model, you see that there is some temperature difference. And of course, you expect the outlet temperature to be more than the inlet temperature. That's why I'm going to invert my block to come with a positive value from my sensor. And that is the result I want. So you see there is 4.694 degrees Celsius or Kelvin differential pressure. That is basically the same. For differential pressures, Kelvin and Celsius are the same. But now let me ask for the absolute temperature of this point. I'm asking for the absolute temperature of this point, and since this pump is not going to change the temperature of the fluid that much, I expect the result to be equal to the reservoir temperature, which is 293.15 kelvins. And I run the model, and you see that this is basically the result I was expecting. But you can see that the description says the physical signal port T is in kelvins. What if I want to see the result in Celsius? Again, I go to the PS Simulink converter, and the symbol for degrees Celsius, if I look at this list, is you see that it's deg C. This is the symbol for degrees Celsius. So I double click on the PS Simulink converter and I ask the result in degrees Celsius. Now I run the model again, and to my surprise, the result did not change. Why is that? You can see that in the description it says apply affine conversion checkbox is only relevant for units with offset, such as temperature units. So when you have temperature units and you want to convert temperature units, you need to check the apply affine conversion. And it is talking about an offset. I want to tell you what it means by offset. You see, when you're, for example, converting pascals to kilopascals, so 1 kilopascals is equal to 1000 times pascals. So when you are going to convert pascals to kilopascals, you just need a multiplication factor for conversion. And this is basically the case for most of unit conversions. That goes the same for cubic meters to liters. For example, 1 cubic meter is equal to 1000 liters. So the conversion factors are always just a multiplication, but that is not the case for temperature. So Kelvin is equal to degrees Celsius plus 273.15. And this addition is called by MATLAB an offset. And when you are having an offset, you have to check the apply affine conversion. I can see that I have only seen using this checkbox for temperature units. I have not used it for any other units, and I think you're not going to use that either. So now if I run the model, now it is 20 degrees Celsius exactly. That is the result I was expecting. And that was pretty much most of the sensors that you're going to use most of the times. Temperature, pressure, and flow rate. These are the three mostly used sensors of liquid systems. But just to make my discussion complete, I want to talk a little about two-phase fluid systems. So let me look for turbine. Here's a two-phase fluid turbine. And I need two reservoirs for it. So the turbine inlet and outlet are going to be connected to two reservoirs. I set some common values for turbine inlet and outlet. I set the inlet to 60 bars and the temperature to, let's say, 300 degrees Celsius. And I set the turbine outlet, which is basically connected to the condenser. I set it to 7 kilopascals. Again, it is a common value. For a condenser to be at 7 kilopascals, it is just so usual. And one thing you may want to know is that for outlet reservoirs, the temperature is not going to be important, since the temperature of the fluid going into the reservoir is going to be calculated based on the upstream blocks. And if you change the temperature of this reservoir, it's not going to change any of your results. And I have to convert the rotational ports of turbine to somewhere. I'm not going to go through a deep discussion of that. For now, I'm going to connect it to the sources and sensors. So here's an ideal torque sensor, and the rotational reference, the mechanical rotational reference. I connect the casing and the sensor to these blocks. Then I need the solver configuration block, and I have to look for the utilities. Here it is, the two-phase fluid properties. Now I run the model and I see that it runs perfectly. So here under the sensors, I want to talk about the vapor quality sensor. So I connect the inlet and outlet of the turbine to vapor quality sensors. And vapor quality is basically a dimensionless parameter, so it has no units. Before I run the model, I want you to take a moment and think about the result you're going to expect. The turbine inlet is a superheated fluid, and the outlet is, I am expecting it to be two-phase. The outlet is going to be in the saturated position. So that's it. That's basically the result. The inlet, it says the quality is 1. When it says 1, it means, it does not mean that it is a saturated liquid of basically only a steam. It means that it is probably a superheated steam. And if it showed a value of -1, it means that it is, the fraction is undefined. Maybe it is subcooled or something. So, but the turbine outlet is in the two-phase fluid part of the diagram. And this is the vapor quality of the outlet. And there are so many other sensors to look for. Here, if I double click on it, I can see that there are enthalpy, density, specific volume, and entropy of the system ready to be displayed. So I connect the turbine outlet to this kind of sensor, and I ask for all of these 4 parameters. I run the model, and here is the enthalpy, here is the density, next one is entropy, and the next one is a specific volume. And you want to make sure that you are correct with the units. So this sensor sends the enthalpy in kilojoules per kilogram, sends the density in kilograms per cubic meters, sends this specific volume in cubic meters per kilogram, and the entropy in kilojoules per kilogram Kelvin. And that's it for today. I hope you enjoyed this tutorial and learned something. If you have any ideas and comments, let me know about it. I cannot wait to hear from you, and see you again next time. Bye bye.